All right, welcome for lesson 4.3, which is solving exponential equations. Big, long 3-minute review, and so we're going to bring up a few points in this 3-minute review and eventually get into the goal at hand, which is exponential equations. Some of the exponential equations that we'll see will be review, and some will be brand new, and maybe solve some of our problems that we've been thinking about for quite some time about exponential equations. Anyway, the 3-minute review, the first one is just a graphing exercise. This is the basic log graph, base 4, and we see we moved it up 1 here. That's the idea. Remember, the basic log graph goes through 1, 0, and then the base 1, and flip of the base, -1. This is just the exponential function base 4 that would be over here reflected, and hopefully we're getting pretty good at graphing these basic log functions. And I just move it up 1. Easy, right? Just move everything up 1. Dandy. Easy peasy. And this is y equals 1 plus, but we could write it the other way. I think I wrote it this way so we didn't get confused that the 1 was in with the x. This was a vertical translation up 1. Rather than this one, which is one of these hard ones, right? When I got a factor of 4 in with the x, it's opposite that we think. So this is a horizontal compression factor 1/4. So that means all of the horizontal distances are cut in a quarter. So, all right, well, I'm going to start with my nice starting spot. A quarter is about, it would be a half, a quarter's there. See, this one's not bad. It was 4. It gets squished to 1. This was a quarter. It gets squished to a quarter as much as that, almost 0. I wish I had more graph to show here, but what would happen here? The next point out here would be the next power of 4. This would be 16, out 16 and up to 2, squished back, not 16, but 4 2. It would actually be right there, wouldn't it? This point's not on my black graph there, but just if I think about it now, look what's happened here. Look what's happened. You see? These are the same graphs. Wow. What's happened? Can you explain what happened here? Well, have a look. This thing is log base 4 of 4 to x. When I'm multiplying two things inside a logarithm, I can split it up by adding, right? This is what we learned last day. What's that? Log base 4 of 4 is 1. Okay. Dandy. So that means that's why they're the same thing algebraically. It says now graph these. Perhaps think of a way to simplify the function first. I'm going to allow you to do that, to graph those. Now that you've seen the trick, you might want to pause the video and try them. I'm actually not going to do the graphs in this video. If you remember to ask me to post the solutions, I'm going to show you the algebra here real quick, because I don't know some of these graphs, but certainly I could use a log rule, make it something more familiar. Then this is easy. This horizontal compression by factor 1000, no thank you. I think what I'll do is I'll split this up, and then log base 10 of 1000 is log base 10 of 10 cubed, and then this is just up 3, right? Function composed with its inverse. I think I can do this, but if you would like to see the graphs, ask and I'll post those for you. I'm not going to go over the graphing in this video. Basically, I want to show you a use of that log rules. What's next? I think we're leading into some exponential equations. This is like a grade 11 one. How we did this, we noticed that 128 is a power of 2. So I actually can write this side as 2 to the exponent something. I just got to figure out what. and I can guess and check on my calculator, or I just sort of count up by factors of 2. That's the way I like to do it. 2, 4, and I'm counting on my fingers. You can't see that. That's 2. That's 2. Double that makes 8 is 3 2s. 16 is 4. 32 is 5. 64 is 6. 128 is 7. And check that on your calculator. Then I can see two bases with the same power have the same exponents. Therefore, this is grade 11 style. Grade 11 style. I want to show you a grown-up version of this. Okay? We know that to get the unknown out of the exponent, I can do the opposite operation. I know what the opposite operation of log base 2 is now. It's exponential function base 2 is log base 2 of both sides, right? On the left-hand side, I have a function composed with its inverse. This wipes itself out, and I'm just left with what was up in the exponent, which was x, and then this becomes one of these log evaluation things that we've been doing for a few days now is still 7. This is a grade 12 version, isn't it? Do I care which version you do? Essentially, they're the same, right? It's knowing that 128 is 2 to the exponent 7. Similarly here, I'm going to actually just do the grade 12 version, okay? Log base 3 of 3 to the exponent x equals log base 3 of 1 over 81. Now I know on the left-hand side, function composed with its inverse, I'm just left with x. On the right-hand side, I've got 1 over 81. That's 3 to the exponent something, right? Well, negative exponents mean fractions 1 over, and 81, I think, is 3 to the exponent 4. 3 times 3 is 9, times 3 is 27, times 3 is 81. Yep, x is equal to minus 4. Okay, now this one. This one, remember, when we got to these sort of questions in the review, and when we, the preview, rather, review of grade 11 stuff back in grade 11, this was kind of a pain, right? Because this isn't a power of 2. This isn't 2 to the exponent something. In fact, 2 squared is 4. 2 cubed is 8. I know it's somewhere between there. Maybe I'd guess 2.5. X is 2.5. But I'd be off guessing and checking. This is not much fun at all. Notice here that you say, okay, well, we've learned something since then. Let's just take the log base 2 of both sides. All right? Log base 2 of both sides, and I see, there we go. Function composed with its inverse. This gets wiped out, and I'm left with x. On this side, I have the log base 2 of 6. And here, to solve this, I need to write 2 to the exponent something. I'm still stuck here, right? This is the same problem written in a different way. We need to figure this out. I thought we were there, but, well, what would be a good base to take the log of both sides? Maybe something we can use our calculator on, right? So for instance, instead of log base 2, which I can't put that into my calculator, why don't I take log base 10 of both sides? Well, why is that better? Well, this is a number on your calculator, right? I could pound that into my calculator and get a number. What happens on the right side? Well, this isn't a function composed with its inverse. The bases are different, but there's still something I can do, right? The exponent gets written in front. And now this is just a number, and I can divide by it on both sides, and I get log base 6, or log base 10 of 6, button on your calculator, over log 2, and this I can put into my calculator, and that is about 2.585. Check it on your calculator. So now suddenly I can get this very quickly using any base. In fact, this sort of technique, notice what I've got here, log base 2 of 6 is equal to the log of 6 over the log of 2. Log of the thing over the log of the base. This is a good formula. Not with 6s and 2s, but with any base in anything, we can actually calculate this now. And that's where we're started today's lesson with what's called the change of base formula. Um, or if I had the log base A of something, it's the log of the something over the log of the base. Notice the log of the base goes on the bottom. And so here, if I wanted to do this question, this log base 2, sorry, 2 to the exponent x, we've did that already. And we know that x is equal to the log base 2 of 6, but we also saw that it's equal to the log base. This is the same question that we just did. Um, and so I can do this really, really quickly on my calculator. Probably that's what my, evaluate log base 7 of 13.2. And notice I can't do this in my head. This thing is 13.2 isn't a nice version of 7. You know, I know if that 7 to the exponent 1 is 7 and 7 squared is 49. So I know the answer is between 1 and 2 and probably closer to 1. I might guess 1.1 or 1.2, but this would be guessing and checking like a grade 11 would do it, but we're smarter than that now. We know it's the log of 13.2 over the log of 7, bash that into a calculator and get an approximate answer. I get 2.64 about. And practice this on your calculator, folks, okay? How are we making out for time? Are we getting close to the 10-minute mark? We are. I'm going to stop there, and we'll pick it up for example 3, which is a bunch of equation solving in part 2.